Hello, everybody. Uh, so let's continue chapter 7. This is actually my last presentation for chapter 7. So, in previous lecture, we discussed the isentropic efficiencies of steady flow devices. For turbine, you say that the isentropic efficiency is actual work over isentropic work. Or if you have, the Muller diagram, HS diagram, uh, you can actually calculate, the vertical distance between point 1 and point 2 for the for the isentropic, process, and for the actual process to calculate the delta H. So for the compressor, based on the definition, the isentropic efficiency equals to the isentropic work over actual work. Or by using the enthalpies, you can write the isentropic efficiency of compressor is H2S minus H1 over H2A minus H1. The H2S is, I'm sorry, the H2S is the enthalpy for the exit enthalpy for isentropic compressor, and H2A is exit enthalpy for actual compressor. So H1 is the same, in both these two, denominator and numerator. So for pumps, you can use this equation to calculate the isentropic efficiency, and then for nozzles, we have two actual equations to calculate the isentropic efficiency of nozzles. The, actually, based on the definition, the isentropic efficiency of nozzles is actual kinetic energy at nozzle exit over isentropic kinetic energy at nozzle exit. Or you can use the velocities, the actual velocity in the exit square over the isentropic efficiency in the exit square. So you can actually use this equation for all cases, for all nozzles. If we assume that the inlet velocity is negligible in comparison with the exit velocity, then yeah, we can prove that you can use this equation to calculate the isentropic efficiency of nozzles by using the enthalpies. Again, H1 is the enthalpy in the inlet of nozzle, H2A is the enthalpy in the exit of actual nozzles, and then H2S is the enthalpy in the exit of isentropic nozzles. So, what is the application of isentropic efficiencies? So, um, look, guys, we the actually the isentropic efficiency is the maximum efficiency for steady flow devices. So we prefer actually to design devices, steady flow devices that are close to this isentropic efficiency. So keep in your mind that the isentropic efficiency for steady flow devices for irreversible process are always less than 1. Isentropic efficiency for steady flow devices for reversible and adiabatic process equals to 1. And if you have isentropic efficiency higher than 1, or somebody claimed to design a steady flow device with isentropic efficiency more than 1, it's impossible. So we have actually two applications for the isentropic efficiency. The first one you can use to actually verify the some claims. For example, if somebody claims to design a compressor with the isentropic efficiency of 1.5, this is impossible. This claim is actually is not valid. This is the first application. The second application, if you have let's say two different steady flow devices. For example, you have compressor A and compressor B, and then the isentropic efficiency for compressor A is 0.7, and for compressor B is 0.8. You should select compressor B because compressor B has higher isentropic efficiency. meaning that this compressor has actually less losses. So two applications. You can actually verify some, claims about the steady flow devices, and the second one, you can actually select, the steady flow devices with higher, actually with less, losses or better, performance. So these are two applications for the isentropic efficiencies of steady flow devices. Let's go over three examples, and then this is actually, the remaining part of my lecture. I will go over three examples. So for the first one, please open the guided note available on the blackboard. The first one is about a claim of actually regarding the steady flow, regarding a adiabatic steady flow device. So an inventor claims to have invented an adiabatic steady flow device with a single inlet outlet that produce 200 kilowatt when expanding 1 kilogram. So we have the M dot, the fluid is air, and then we have the inlet pressure, temperature, and the exit pressure. So the question is this claim valid? So to answer to actually to solve this problem, um, we need to answer to this question. The first thing is that what is this steady flow device? We have no information. We have no clear information, no clear statement about this, steady flow device. What is this steady flow device? And then the second one, what is the unknown parameter? So how do you want to actually verify this claim? So you need to answer this question before you uh, solve this problem. So please pause this video, spend 2 minutes, and then think about these two questions. Okay, so look guys, this is actually, let's go over, the available information. So the first thing is that this is a steady flow device, and then there's one inlet and one outlet, and then we actually this, device produce or generate W, correct? So generate W, and then what happened? The pressure decreases, correct? Look, the inlet pressure is higher than the exit pressure. So this is a turbine. This is a turbine, correct? Because we have actually the pressure decreases and also, W generated. So this is a turbine. For the second one, what is the unknown parameter? I just discussed, two application for, isentropic efficiency. The first one, we can actually verify this claim if you calculate the isentropic efficiency of, this turbine. So if you calculate the isentropic efficiency, then you can actually make a decision if this is a claim valid. So this is a turbine, and then we need to calculate the isentropic efficiency. So as the first step, uh, please complete this, table. I added, some information. This is the air. So state one, state two, and then please spend, 2 minutes, pause this video, and then complete this table. Okay. So here is, the table. I just complete the table. So you have the temperature, you have the pressure for the inlet. So we have the W out actual. This is the W dot actual. And then this is not the lowercase. This is actually, the total W. We have the M dot, we have the P2, and then the isentropic efficiency of this turbine is not known. You need to calculate the isentropic efficiency of this turbine. Now, to solve this problem, you need to actually follow these three steps. First, you need to find equation. What is the best equation to find, the isentropic efficiency of this turbine? This is the first one. Then you need to find some parameters, some unknown parameters, and then eventually you can calculate the isentropic efficiency of this turbine. So please pause this video, spend 5 minutes, and then try to find equation, then find the unknown parameters of that equation, and then eventually calculate the isentropic efficiency of this turbine. Okay, so yeah, based on the definition, the isentropic efficiency of a turbine is W actual over WS. The W actual is given. You have the W actual. It's 230 kilowatt. So what do you need to do? You need to calculate the isentropic W, correct? So how we can calculate the isentropic W? To calculate the WS, you can write the first thermodynamic law for an isentropic turbine, correct? So what is the first thermodynamic law for isentropic turbine? Please pause this video, spend 2 minutes, and then just write the first thermodynamic for isentropic turbine and then simplify it. Okay, so look at this, the first thermodynamic law for steady flow devices with one inlet and one exit. So keep in your mind that, guys, look, I just wrote this equation for isentropic turbine. Why? Because I consider the W dot S, the isentropic W, and also the exit isentropic enthalpy, and then velocity for isentropic turbine. Actually, exit velocity for isentropic turbine. So again, W is the W dot S, enthalpy is enthalpy for isentropic, and then in the exit, and then exit velocity is velocity for isentropic turbine. If you want to write this equation for an actual turbine, you should write here W dot A, H2A, and then V2A S squared, correct? So the difference between the first thermodynamic law for isentropic turbine and actual turbine is in W dot enthalpy in the exit and velocity in the exit. So let's simplify this equation, for an isentropic turbine. For isentropic turbine, based on the definition of isentropic process, is adiabatic and reversible. So Q dot net is 0, correct? We are looking for the W dot S. We need to keep it. And then we can actually cancel, the kinetic energy and potential energy changes. And then you can write the W dot S out equals to the M dot H1 minus H2 S. And then you can use, the CP average to rewrite that equation into this format. Okay, now, so look, guys, M dot is known. We have the M dot. What you need to do, you need to find the CP average. To find the CP average, you need to have the isentropic temperature in the exit, or T2S, correct? So the first step, what you need to do, you need to find the T2S. Please pause this video, spend 2 minutes, and then calculate the T2S. I try to calculate, the W dot S by using both these two equations, and then we can compare the results. So in this step, I try to use, the M dot CP average T1 minus T2S. Pause this video, spend 2 minutes, and then calculate the T2S. So to calculate the T2S, guys, if you remember, for ideal gas with isentropic processes, we develop, several equations. And then if you assume that, we have the C, actually the constant, sorry, average, or constant, heat capacity, we can use, this correlation by having the pressures to calculate, the T2S. So T1 is known, P2 is known, P1 is known, and then you can find K for the air from the reference table. I think it's 1.395 or 398, and then keep in your mind that the temperature must be absolute temperatures. So yeah, K is 1.395, and then you have the pressure, you have the temperature. If you substitute into this equation, you can find the T2S. Now you have the T2S. To calculate the W dot out, you need to find the CP average. So to calculate the CP average, you have the T1, T2S, and then you can find the CP average. Please pause this video, spend 1 minute, and then find the CP average. Okay, to find the CP average, first you need to calculate the T average. So we have the T1, T2, and then you can calculate the T average. Then you can use table A2, and then this temperature is between 400 and 450. You can use interpolation to find the CP average. Now you have everything, and then you can find the W dot S, correct? So the CP average is known. You have the M dot is 81 kilogram per second. T1 is known, T2S is known, CP average is known. If you substitute here, you can calculate the W dot S, or W for isentropic turbine. So now you have the W for isentropic turbine, you have the W for actual turbine, and then you can calculate the isentropic efficiency. The isentropic efficiency of this turbine is 0.781. Question. Now, what's the conclusion? What do you think? Please spend 1 minute, and then, what do you think, if this claim is valid or it's not valid? Okay, guys, based on, our, discussion, uh, this actually isentropic efficiency is less than 1, so this claim is valid. So you can calculate this, W by using the m dot H1 minus H2S. How? If you want to calculate the H1 and H2, you need to use table A17. So the T1 is now 573. So 570 is here, 580 is here. You need to do the interpolation to find the enthalpy. So this is the H1. So the T2S is now and then you can actually find the H2. This is the H2, guys. It's a typo. So again, you need to do the interpolation to find the H2. You have the M dot H1 and H2S, and then you can find the W dot S for isentropic one. So this is pretty close, guys, to the value that we calculate actually by using the CP average. And then the isentropic efficiency by using this method is 0.779. Again, the isentropic efficiency is pretty close to that value that we calculated by using the CP average. So the claim is valid. Okay, so this is the first one. Let's go over the second problem. So for the second problem, there is air with 500 kilopascal. We have the inlet pressure, we have the exit temperature, and then there is adiabatic nozzles, and we have the inlet velocity, and also we have some information for the exit, and then you are asked to calculate, to determine the isentropic efficiency of these nozzles. How? By using variable specific heats, by using this method. Also exit velocity and entropy generation. So look, guys, because we have this actually figure, and everything, all information are available on this figure. So I just skip that step 1 to make a table, and then just collect all available information. So you can skip that step. Everything is available here. So to find the efficiency, isentropic efficiency, and exit velocity, what you need to do, you need to write the equation. Then when you write the equation, you need to just find the unknown parameters, and then eventually you can calculate, the isentropic efficiency of, these nozzles. So this is the 3 steps. So please pause this video, spend 5 minutes, write equation for isentropic efficiency of nozzles, and then calculate the require unknown parameters, and then eventually calculate the isentropic efficiency of these nozzles. Okay, look, guys, to actually for the isentropic efficiency of a nozzles, you have actually we have two different equation. This one is the exact value, and then the second one is if you assume that the inlet velocity is negligible in comparison with the exit one. Based on this actually exact solution, what you need to do, you need to find the velocity in the exit, correct? You need to find the actual velocity and isentropic velocities. So to find the velocities, what you need to do, you need to write the energy balance for this nozzles. So please write the first thermodynamic law for these nozzles and then simplify it to calculate the actual velocity in the exit. Please pause this video, spend 2 minutes, write the first thermodynamic law for an actual nozzles to calculate the exit velocity in the nozzle. Okay, guys, this is the first thermodynamic law, correct? So again, what is the difference between this actually energy balance equation for actual and isentropic one? The three differences. W, correct? So this is the actual, so this W is the actual W. H2A, this is the actual enthalpy in the exit, right? And then the velocity, you need to find the exit velocity for actual nozzle. So again, if you need to write this equation for the isentropic nozzles, then this W will be the W dot S, you know uh, work for isentropic nozzles. This will be the exit enthalpy for isentropic nozzles, and then this will be the exit velocity for isentropic nozzles. Okay, so if you want to simplify this, equation, the first thing is that um, this is the adiabatic nozzles, correct? It's adiabatic, so you can cancel Q. So there is no W here, for these, nozzles. And then you need to keep enthalpies, and then you need to keep the velocities, and then you can cancel the changes in potential energy. And then based on this correlation, we can find a real actually equation for actual velocity, correct? So to calculate the actual velocity in the exit, to calculate the exit velocity for actual nozzles, what you need to do, you need to have the inlet velocity, it's available. You need to have the enthalpy in the inlet, you have the temperature, you can find the enthalpy in the inlet, and then you need to find the enthalpy in the exit. So you have the temperature, correct? This is the temperature for a actual turbine. So you can, actual, nozzles. So you can find the H2A. So this is the first method. You can use table A17 to find, the enthalpies. So the first temperature is, 400. So from the 400, you can find, the H1. You can report, the S01, and also you can report the PR1. We will use, this information in the next actual, steps. So for the second one, you have the temperature is 350, so you can find the enthalpies and S naught in the for the second actually step. Now, so from here you can calculate the actual the exit velocity for actual nozzles, correct? You find the enthalpies, and then you can simply find the V2A. Now you have the V2A, correct? You can calculate, sorry, you have the V2A, correct? So to calculate the, isentropic efficiency, you can use two equations. If you assume that the velocity in the exit is negligible with respect to the velocity in the exit of these nozzles, here this is probably a good assumption because the inlet velocity is 30 the inlet velocity is 30 meter per second and the exit velocity is almost 320. So probably this is a good assumption. So you can actually use this equation, the second equation, to calculate the isentropic efficiency of nozzles, correct? So if you want to use this equation to calculate, the isentropic efficiency of these nozzles, you need to have the H1, you already found the H1, you need to find the H2 for the actual, nozzles, you already found it, correct? And then you need to find the H2S, correct? The an exit enthalpy for isentropic nozzle. So please pause this video, write the first thermodynamic law for an isentropic nozzles, and then calculate H2S. Or you can just use any other method to find the H2S. Just pause this video and then try to calculate the H2S. Okay, so look, guys, for ice, this is the isentropic process. You want to calculate, the exit enthalpy for isentropic nozzles. So for isentropic nozzles with variable specific heats, keep in your mind that in the problem statement you are asked to calculate to use the variable specific heats. So for the variable specific heats, you can write from the previous lecture. You can write the P2 over P1 equals the PR2 over PR1, correct? So P2 and P1 are known. You have the PR1, correct, for the T1. So from here you can find the PR2, correct? Now you have the PR2, and then you can find the H2S, and also you can find the T2S from table A17. So the PR2 is 2.28, 2.28. So it's between 340 Kelvin to 350, and also between these two enthalpies. By using the interpolation, the H2S will be 346.33 kilojoule per kilograms. Now you have the H2S, and you can simply calculate the isentropic efficiency of these nozzles. So this is the isentropic efficiency of these nozzles, 0.9235. How? By assuming that the inlet velocity is negligible. Now let's use the first equation to calculate the isentropic efficiency of nozzles. Keep in your mind that it equals to the V2A squared over V2S squared, correct? And then we can compare the results with this correlations. Now, so this is the second, actually, the first, method, the first, the second method, to calculate the, the isentropic efficiency. This is the accurate solution. This is valid for all, nozzles. So, what you need to do, you already calculate the exit velocity for actual nozzles. We wrote the first thermodynamic law, and then we simplified to calculate the V2A. So please spend 2 minutes and then try to calculate the V2S squared. I mean the exit velocity of isentropic nozzles. So if you want to calculate the exit velocity for isentropic nozzles, you need to write the energy balance, the first thermodynamic law for isentropic, process. Again, look, guys, the difference between the energy balance of first thermodynamic law for isentropic process and actual one is in three terms: W, um, velocity in the exit, and enthalpy in the exit. So Q is zero, there is no W, you can cancel the changes in, potential energy, and then you can actually write, this equation to calculate, the exit velocity for isentropic nozzles. So you already found the H2S, correct. We already found it, in the previous section. And then you have the V1 in the, problem statement. You found the H1. From here, you can find the V2S. By now, by using this equation, you can find the isentropic efficiency of nozzles, which is 0.925. And then this is the results. This is the summary. Look, I use the exact solution by using the velocities to calculate the efficiency of isentropic efficiency of, this is the nozzle, it's the efficiency of nozzles, not turbine. And then the second method, we assume that the exit velocity negligible inlet velocity. I will fix this problem in the my in this typo in my actual PowerPoint. This is the negligible inlet velocity, not the exit velocity. So yeah, and then look, the results are pretty close by using these two different methods for this specific problem. Now, for the last part, you are asked to calculate the S generation. Please spend 5 minutes to calculate the S generation. What you need to do, you need to write equation, you need to find the unknown parameters, and then you need to calculate the S generation. Pause this video, spend 5 minutes, and then calculate the S generation. Okay, so based on the definition, the S generation is a combination of the delta S for system and surrounding. So you need to calculate the delta S of air and delta S for surrounding. For the delta S of air, you actually have, two different equations. Here you are asked to use, the variable specificates. So you need to use this correlation. The delta S of air is S naught 2 minus S naught 1 minus R ln P2 over P1. So you can find the S naught 2, S naught 1, from the table, um, um, I think A17, and then you have the pressure. You need to find the R for the, air, and then you can calculate the delta S air. The next step, you need to calculate the delta S surrounding. Please pause this video, spend 2 minutes, and then calculate the delta S of surrounding. So the delta S for surrounding is 0. Why? Because for the delta S of surrounding, you can write the delta S equals to the Q over T. And then this is the adiabatic process. Q is 0. So the delta S surrounding is 0. And then the S generation is this value. This is the positive value. So you are actually right. Keep in your mind that S generation can't be a negative value. Okay, and then the last question, we have a piston cylinder device, and then this piston cylinder device, goes under three reversible thermodynamic cycles. Here we have, the information from this is the PU diagram. From point 1 to point 2, it's a constant temperature process or isothermal, and then from point 2 to point 3 it's a isentropic process, constant S, and then from point 3 to point 1 is constant pressure. So if you have some information, you can just make a table to add all this information. You are asked to find the by using the variable specific heat, you need to calculate work and heat for each process. So uh, this is a piston cylinder device. So it's a closed actually device. So or closed system. What we need to do, we need to write the energy balance. The energy balance for this closed system is Q net minus W net equals to the M delta U. So let's start from the first, process 1 to 2, and then calculate both work and heat. So for the first, process, let's simplify, this, the first thermodynamic law for process 1 to 2. Please spend 2 minutes. What do you think? And then simplify, this first thermodynamic law for this, process 1 to 2. So for process 1 to 2, the fluid is air. So if you assume that this is the ideal gas, then the delta U depends on the temperature. Temperature is constant. You can cancel the delta U, and then you can write Q net equals to the W net. Correct? So if you can calculate Q net or W net, you can calculate the other one. So please spend 2 minutes, pause this video, and try to calculate either Q net or W net for this process. Okay, so for this case, because this is a constant temperature process, you can use, this equation, the delta S equals to the Q over T naught to calculate the Q. So if you can calculate the delta S of air, for process between 1 to 2, you are able to calculate the Q. Please pause this video, spend 2 minutes, and then calculate the delta S. So if you assume that we have variable specific heat, you can use this equation to calculate, the delta S for air. So here the temperature is constant. So the first term will be 0 because S naught depends on the temperature. And then you need to find the R for air, P2 and P1 to calculate the, delta S. Also, you need to multiply it, by the M to calculate the total delta S. So P1, V1, and T1 are known, and then by using the ideal gas equation of state, you can find the M. And then from here, P1, P2 are given, you can calculate the delta S, and then if you multiply this delta S by the temperature is 300 Kelvin. Again, keep in your mind that this temperature must be absolute temperature. You can calculate the Q, and then Q equals the W. You can calculate the W. This is the Q and W for process 1. So for process 2, please spend 2 minutes and then simplify the first thermodynamic law for this process. Okay, this is an isentropic, process. Based on the definition, isentropic process are a reversible and adiabatic one. So you can cancel the Q. Q is 0, correct? So W net equals to the M delta U. What you need to do, you need to find the delta U. You already determined M in the previous, section. M is constant because this is a closed system. What you need to do, you need to find the U3 and U2. Please spend 2 minutes and then calculate U3 and U2, find the U3 and U2 from the reference tables. Okay, so to find the U3 and U2, we have the T1. T1 is known, and then we know that the process 1 to 2 is isothermal process. So T1 equals to the T2 equals to 300. So we have the T1, and then temperature is known. You can find the U1, which is equals to the U2, and then you can find the S naught, and then the PR1 and the PR2. So you found the U2. To find the U3, you know that this is the isentropic process, correct? So for the isentropic process with variable specific heat, you can write P3 over P2 equals to the PR3 over PR2. You have the PR2, you have the P3, P2, you can find the PR3. Now you have the PR3, correct? This is the 3.69. 3.69 is between these two values. So by using the interpolation, you can find the T3 and also you can find the U3. Now you have the U3, you can simply find the W for this process. And then the last one is a constant pressure process. Please simplify the first thermodynamic law for this process. Okay, for this process, guys, you need to keep everything, correct? We have Q, W, and also the M and delta U. So now To calculate Q or W, if you calculate Q or W, then you can use this equation to find, um, the other one. So here the process is a constant pressure process. For a constant pressure process, you already learned that the W is P times, delta V, correct? So if you have the P3, V3, and V1, you can simply calculate the, you know, W. So by using the ideal gas equation of a state, you are able to calculate the, volumes, and then from here you can find the W, and then from the W, by using the first thermodynamic law, you can find the Q. So you just started, the application of, the isentropic process. Now you have more tools, guys, to calculate, to actually analyze, process. Just use, the table A17 to find, for example, the isentropic, temperatures, some actually have more tools to solve the problems. Please study the following examples, 7.1 through 7.16. We done with chapter, 7. We will start chapter 9 in the, next lecture. Thank you so much and have a great day.